Hello again. Tonight is kind of a part two of something that I did a few months back on. I was trying to measure or quantify or detect radiation reflection pressure. There were some problems with the presentation, some things I had to correct. So this is kind of a part two, and you may not have seen the part one. So there'll be a little refresh at the beginning. There's some updates, and then the actual meat of the presentation is actually detecting it and confirming it and corroborating it, all that stuff. So it's going to be minutia filled, and there'll be science and technology. We're actually going to have data at the end that measures that photons can push on stuff, control flows of photons. If you get this presentation and you want to just skip to the part two kind of thing, there's a hyperlink in the PDF, that little green arrow, and you can jump ahead. The biggest change between part one and part two is the thing that produces the photons, the particular kind of red, green, blue LED I was using. I switched from a thing called a NeoPixel to a thing called a DotStar. We'll get into the details of what that means but it was basically the NeoPixel was affecting the ability to reliably record the microphone audio. But we'll get into the details of the electronics and soldering and writing software coding in Python, the actual measurements, using the software to generate the data for the measurements, the audio waveform analysis, and then the conclusions, the Eureka moment, as the saying goes. And then, okay, now that you've done that, what do we do next? So it's kind of always been my thing that I've looked at radiation reflection pressure, which is a photon reflecting off of something transfers a portion of its energy as momentum to the thing that it's reflecting off of. And yeah, it's infinitesimally tiny on a per photon basis. But collectively, when you have lots of photons, it's demonstrable that it can move things. And the two that come to mind are the lasers at the LIGO gravitational wave detector. When they upgraded from 30 to 45 watt lasers and they turned the laser on, the interferometer detected a gravity wave because the light beam from the laser moved the roughly 120-pound mirrors at the nanoscale. You couldn't visually see the mirror move or swing or rattle about, but it did electronically. And so they said, so when we turn the lasers on, we should let them dampen the mirror out a bit. So not only did it move the mirror coming back up against the beam of photons, actually that force was being used to dampen the movement of the mirror. And the second thing is there's a Nobel Prize, I think it was 2018, for something called optical tweezers. And they use very low power lasers, not to vaporize viruses and bacteria, but to scoot them along inside of X-ray tunneling microscopes. So you're not going to stick probes in there when you're talking about things at the nanoscale level. So they use little bumps from the light force to move it one way or the other. They're a real thing. It's just, it's so small. How could it ever prove to be useful? I don't know. Nobel Prize and moving 100+ pound mirrors. How do you prove it? By having something measured, a scale that says, I can measure this force, when it's individually billionths of a Newton of force. And even when you turn it up and you say it's a very bright light source, it's still not very much. Plus, as you turn up the wattage on the LEDs, now you've got to liquid cool the LEDs to keep them from frying themselves. So I was looking for, how do you do this? How do you measure it? How do you detect it, confirm it? Inexpensively, on a small scale, and with confirmation using real data. So that's literally what this is producing the photons, measuring their effect, identifying anything that might be discounted as the real cause of it, and then saying, well, what you've got left is I turn the photons on, you see the effect, there you go. So how I connected the dots was, there are these kinds of microphones, and these are very popular microphones. They're in your mobile phone, they're in your laptop, they're in your tablets. It's the predominant microphone in personal electronics technology today, and it's called a MEMS-based piezoelectric microphone. There's a nanoscale level piece of zinc oxide inside this chip, and the acoustic waves, like air hitting this little tiny chip, produces a voltage due to the piezoelectric effect. And that's where you essentially affect force upon crystals, and the crystals produce electrons, and the electrons are voltage. So a MEMS microphone, a micro electromechanical microphone. And these are relevant in everything that you do today that has a microphone in. So I said, well, what if instead of air producing the piezoelectric effect and a voltage, you had light that was hitting this little zinc oxide membrane and producing a voltage? Would that be detectable? And if it's detectable, could I tell what color light, what energy level of photon was hitting it? Could I see in the amplitude of the signal coming back? So those are the things I was trying to prove. Is it possible to detect that I'm doing it? And then when I'm doing it and I change the color, can you see a difference in the signal amplitude? So that's what I was trying to prove. So here's the microphone. The microphone itself is about the diameter of your thumb. Just think of it as a little disc about the diameter of your thumb. That's the printed circuit board. And then in the center of it is this little tiny chip. And the top of the chip is sealed. It's kind of an air reverberation chamber. And then on the bottom of the chip, there is a little tiny hole. And that's where the air pressure goes in to make the piezoelectric effect work, to make it record the audio. And you can see on the bottom of the circuit board, there's a little microphone icon and a little black hole there. That tiny hole, and remember the circuit board is the diameter of your little finger, your thumb. And that's where the acoustic wave from sound goes in. This microphone is so sensitive, I had to turn down a fan in my garage that was 30 feet away because it was picking up the fan sound. Very sensitive microphone. It records the audio at 44.1 kilohertz, which is good for voice, good for music. It's normal sound range. It records them as 24-bit samples. So the height is, 12 bits above zero, 12 bits below zero, 24 bits of signal. There's a lot of dynamic range. The individual microphones are monaural, one channel, but if you have two of the microphones, they're designed to work together to give you two inputs as stereo microphone, but I only need monaural. So what I wanted to do was decide if this particular microphone technology was sufficient to discern the fact that light is hitting the piezoelectric and producing a voltage, and the voltage was coming out as if it was listening to audio. This is the technical minutia of the science. Photons, their energy level, the forces involved in air. So you're talking about things like newtons and joules and Pascals, and I'm not going to get into the detail of them, but they're just units of measure of various things. They're small, but they are. And sound pressure. I had to evaluate the technology of this microphone as to when air, under pressure, air vibrations of sound, hits this little piece of piezoelectric material, what is the pressure, what is the force against that to do the piezoelectric effect to produce the voltage? What is the pressure of sound waves? So I had to evaluate what is the sound pressure that is the minimum amount that this thing can produce. And then what if I took away the air pressure? What if I said, well, let's stick this in a vacuum chamber. I happen to have a 5-gallon vacuum chamber. I'm not using it for originally intended purpose. I'm using it for science, but think of it as a particular consumable product dehydrated. And I'm not talking about food, but anyway, so I have a vacuum chamber and a vacuum pump. It's a double stage 6 per minute vacuum pump. But if I took away the air pressure, would I still be able to measure it? And it turns out the minimum reference pressure is 20 micropascals. 20 micropascals, which is 20 millionths of a Pascal. Remember, it's a unit of measure. And that's just the air force against this little microphone to be able to pick up its minimum sound level, which is 26 decibels dB. If you're into sound measurement, microphones and stuff, that probably makes sense. But most people would just go, okay, it's a threshold. Did you meet the threshold? Yes, I did. and then calculating, okay, I have a photon, it's at a particular wavelength, particular frequency of light, color of light. How much momentum can it contribute? Remember that a photon at rest has no mass. A photon in motion has momentum, but not mass. So there's a formula for calculating, if I have a photon and I know its wavelength, what is the transferable maximum momentum? So you can measure that. If you're one of those people that doubt that photons can contribute momentum, I would ask you to talk to the people at LIGO in Louisiana and say, did a laser actually move your very heavy mirror? Yes, it did. So this is the level of joules per second per photon. Remember, photons individually are very small, but a multiple watt LED can produce many billions of photons per second. So I picked 3 color channels because I've got red, green, and blue channel LEDs, the wavelength of them in billions of a meter or nanometers. And then if you just took that photon and said, how much energy does one photon at that wavelength have? And you can see that the scale factor is by 10 to the minus 28. Very, very small. Remember, that's per photon. Now, if you don't think that that can ultimately wind up being bright, I would ask you to take a look at your computer display or your TV set. If they are either LED backlit LCD or LED, then the light that's coming into your eyes is courtesy of LEDs producing those little tiny photons, bajillions of them. If you have a 4K TV or display that's 3840 by 2160 in resolution, then the number of pixels you have or the number of LEDs producing white light is 8,294,400, and each of them is 1 watt. And they're extremely tiny and individually not producing very high energy photons, but collectively, sometimes you got to turn that screen down because it's just way too bright white. Now, when the photon is emitted, it has a certain maximum momentum potential, but then it gets involved with things. It reflects off of stuff. And then at what angle it reflects at, you have to take all that into account. So I don't know the actual reflectivity of that little piece of zinc oxide, but I know that zinc oxide is fairly white. So I would think it would interact well with a photon. So let's just assume its reflectivity is 90%, because white means a lot of light is coming off of it, highly reflective. The incident angle, the microphone's here, the light's going into it at 90 degrees. So I know roughly the angle. So if I take that into calculations and I say, I'm going to remove away from that maximum potential momentum the reflection and the angle. Now, what level of joules per second per photon do I have? Oh no, it went way down to times 10 to the minus 60. That's a small fraction of the 10 to the minus 28 is now even smaller. But I'm going to be producing billions of these things. So the minus 60, you're going to take away, it's going to be minus 51 really quickly. But that's still a very small value. So then I have to say, well, if I'm picking it up with a microphone, how do I know it wasn't noise from the microphone picking up audio? Well, I'll stick it in the vacuum chamber. Well, now I've got to judge what is the momentum transfer force of the photons as pressure on the piezoelectric material of the microphone. So I had to go in and calculate the decibel of energy against the pressure, which won't be there because it's in a vacuum. Strangely enough, I didn't have to actually do this because I got results without it being in a vacuum, but I was prepared to put this in the 5-gallon vacuum chamber, draw it all the way down to like minus 29 pounds per square inch pressure, almost zero, and then measure it again. This particular decibel level is not minus 60, it's minus 66. Remember, joules versus decibels, 2 different units. Well, how bright are these LED chips in this DotStar smart device? Normally, you can refresh these particular LEDs about 300,000 times a second. That's if you only have, they're only meant to be in a string of LEDs, like would light up your room or your under of your edge of your home or decorative lighting. And they come in a flexible strip. and you can cut off just one of them and then power and interface with just one of them. And that's what I did, just one out of a string. I had to buy a string of 30 of them, but one of them. How fast can I change the data values? And it turns out I can clock it at 312,000 times a second. I can change the value. I don't need to do that because I couldn't detect that with my microphone, because the microphone is 44 kilohertz and I could change it at 300,000 times a second and wouldn't even see it change. But I needed it such that it was faster than internally the LED of this device does not stay on continuously. So if I set it to a certain level of red, the red LED does not stay on continuously. It actually charges up and discharges a little circuit inside the chip that's producing the light at 1.2 thousand times per second. So it's kind of a charged pulse. You see little pulses of red light or green light or blue light. And the reason is when you produce the photons, the human eye gets like a shock of the photons. And then the human retina gets saturated. And so you don't really need to continuously leave that light on. You can turn it off and on at a higher rate than the human eye refreshes. Therefore, it'll look like it's on continuously when in reality it's not. If you ever take your mobile phone and you try and do a video with a sign that's lit up by LEDs in the background, and you see the LEDs are blinking off and on or flickering, that's because of this energy saving feature of LED transmitters to refresh at a high rate that you can't detect visually. So I can change the value of each of the red, green, and blue channels, and I can adjust the brightness of the chip, 31 different brightness levels from 0 to 31. So I said, I'll make it 31, nice and bright, and then I'll adjust the colors of them. It's powered by 5 volts. There are far brighter LED sources, but I didn't need to get involved in that. If I want to get up there, 12 watts is easily achievable. But if I want to use special LEDs, you can actually get up to 500 watts per device, but it's not a single LED chip. It's an array of them. This is how they get really bright lighting. If you ever pop open one of those light bulbs that you get nowadays for like $6 a piece, inside there's not one LED, there's a ring of LED, little tiny ones. And collectively, each of them is about 1 watt. So there's about 60 of them, and you get your 60 watt equivalent light bulb. Remember, different energy levels produce different amounts of power, different, what they call millicandle levels of luminance or brightness. And then there is an ANSI standard called lumens that is slanted towards human physiology, seeing green better than other colors. So if you look at the table down here at the bottom, this is what my LED produces. The different wavelengths, how bright they are, and then what the lumens is. Interesting to note here is the luminance of blue is only 150 millicandela. The red is 600. That's because the human eye has more of a challenge detecting red than blue. So they have to put in more power to get it to come out brighter. Since green is so sensitive, instead of being 600, it only needs to be 500. But still, blue is so much more energetic, it only needs 150. And you can see over in the right-hand column, the actual luminance, the lumens output of it. And you can see that even though green is reduced over red, it's like twice the lumens of red, because you're looking at this in lumens, human visual perception, and green is so easily perceived by human eyeballs, retina chemistry. So what if I said, I want to send out lots of these photons? What would I now be getting? Well, how many photons per second am I generating in each of the colors? And I had to take the power coming into the LED chip, 0.2 watts is the maximum dissipation. It's at 5 volts. And then I had to split that for the red, green, blue channels. And then I had to adjust that based upon the different luminance levels of the chips. And from that, I can calculate, yes, it is possible to calculate roughly the number of photons per second. So you can see it's plus 16, plus 17. There's lots of photons coming out. And the force, instead of it being minus 60, comes back into the minus high 40s to 50s levels. So it comes up rather quickly. The question is that level of decibels force sufficient to activate the microphone? Well, it turns out it is. I'm not going to hold you up for long, but it turns out it is. So how do I know that it's actually what I'm doing that makes the microphone pick up stuff? So I have a lot of things I have to isolate to say, I've got a value. Is that from me or not? How would I be detecting this by my microphone? The microphone detects two things. It detects the amplitude, the voltage level of the signals, positive and negative, and it detects the frequency, how often the signal amplitude changes per second. I wasn't so much caring about the frequency. I was concerned with the amplitude. So if it's getting a certain level of input and then I crank up my LED, does it go up accordingly? And if I change the color, does the amplitude change in accordance with the energy level of the wavelength of that color? So that's what I was trying to do. But I had to get around things like this, the chip pulsing the LEDs, and then do I actually see that in the data that I'm recording? And, at what frequency can I record changes? I don't want to make my red, green, and blue value changes too fast because then the microphone at 44 kilohertz won't be able to see the difference. I have to make it slower. And then I thought, well, if I really have to prove this out, are my changes in the LED output, my intentional values, are they getting confused with other sources like this pulsing of the LEDs and such? So I said, well, if I encode data on the light signals that I'm sending out, instead of just saying red at this level, I went red. Encode basically data on the level of light that I'm telling it to put out, then I can tell it was me, what I did, versus something else going on. And a good way of describing that is if you've ever gotten pulled over by law enforcement for speeding, and he used radar to detect, handheld gun to point at your car and do radar detection, how do you know that wasn't just stray microwaves coming off of a radio transmitter somewhere? It's because the radar gun encodes the radio signal, it modulates the radio signal with the data pattern associated with not only the radar gun, but like that specific one. It encodes parts of the serial number of the device in the radar signal. So when it picks it up, it can say, not only was it from a radar gun, it was from this radar gun. Because if you got two guys using radar guns and they happen to cross the streams, as the saying goes, then how do you know who was clocking your radar? Well, it's encoded in the signal. I knew how to do that. I would rather not do that, but it was there in the background in case I really needed it. Turns out I didn't need it. So I had to calculate what is the maximum data rate that I can impose or modulate on my signal, and will it pick it up? And so width of the pulses that I would induce would be a prime number. That means it's not normally found in nature. So it would be 71 milliseconds. And what would be the frequency of the data that I was encoding? Turned out it was 3.141 hertz, or times per second. And that happens to be essentially a foreshortened version of pi. So I was using a prime number in pi. If I really had to encode the data, it would be pretty obvious where the data came from. So here's the not detailed, but big picture of it. I have a photon source, the photons come out of it, and they get detected by a force detector. And what that actually turns out to be is, if I was going to put this in the vacuum chamber, then I needed a battery source for powering the computer. The computer was running a Python script. It would drive the photon source, and the photon source would produce photons. They would enter the microphone, and the microphone would send back its audio signal to the computer, and the computer would record it. And then I would be on the outside of the vacuum chamber talking Wi-Fi to the Raspberry Pi computer and sending it commands and controls and looking at status and such. So that was what I was shooting for. Turns out I didn't need the vacuum chamber. It was readily detectable. I'm going to skip over a few of these because it gets into the minutia of how you do things on a Raspberry Pi, all the software I had to make sure I loaded, how I detected it properly. So I'm going to show them, briefly mention them, and then move on from them because I'll pause for a second. You can screen capture it or ask me for the PDF and I will send you the PDF. If it's in a vacuum chamber, obviously I'm not going to be running any cables through my chamber to get to it. So no keyboard and mouse, display, no graphical user interface. It's inside the tank. Talk to it via Wi-Fi. And then the interfaces, how I talk to these various devices, there's different kinds of interfaces for talking to them. And I would be remotely communicating essentially on a Windows computer, talking over the network connection to the Raspberry Pi. And then I would be putting out the LED brightness changes. And I would deliberately pause between making changes. So there was kind of a flat spot I could detect in the signal. I didn't know what level of red, green, blue change was going to be sufficient. So I said, well, I'm going to have to do wide swings. So if you're making little movements, it may not be noticeable. And there was one level at which it wasn't noticeable. We'll talk about that later. But I did wide swings. So I would go from 0 all the way up to 255 and a couple of values in between. So you could see like big wave changes. And I not only had red, green, and blue, but I could turn on all of red, green, and blue at the same time, which was, kind of a white. It's kind of a bluish white, but it was kind of a white. And this one's a little bit of a stretch, but having been aware of what goes on at the National Institutes of Science and Technology regarding time accuracy, gravity comes into effect. And when you can't discount anything else, just assume it's going to be gravity and do something about it. If my microphone was up here and my light source was here, then whatever effect I was detecting, if I turned it this way, people could say, well, of course, Earth's gravity's pulling on the photons, and that's what's causing it to do it. I said, I don't need that kind of hassle. So I turned it sideways. The LEDs are coming out sideways, and the microphone turned sideways. Here's where we start kind of part 2 updates. So the system under test is actually a Raspberry Pi, an LED emitter, and a MEMS microphone. I need to understand how I isolate that from various other sources of interference, and we'll get to the detail of that. But I literally wrote Python scripts that would do things, and when it did it, it would spit out the time of day down to the nearest millisecond, thousandth of a second, and I could see that accuracy when I was recording the audio as waveforms. I did not need vacuum, and I did not need to embed data into the LED stream. So I had to do some soldering. We'll get into the details of that. I used a lot of stuff from Adafruit, their software, as well as components. And I took pictures of lots of things, but since I didn't need the vacuum chamber, I didn't take pictures of what I didn't need. This is the computer. It's about the size of a stick of chewing gum. That size. It's called a Raspberry Pi 02W. It's about $20. It's a gigahertz class computer. It's a quad core 64-bit, very capable little computer. It has a bunch of interfaces on it, some of which I didn't need, like Bluetooth or video interface. Turns out I didn't need it to operate in a vacuum chamber, but it could. Didn't need it to operate on batteries, but it could. I needed to understand like the operating system and the libraries it would use and such. Configuring it and commanding it, I was talking to it over a local network in my house. How to edit configuration files on a Linux-based Raspberry Pi. How the connection was to be. And literally, if you're going to be wiring things up in an experimental way and you're buying the cheapest components you can get off the internet, some of them may not be working right. They may be dead shorted, in which case it might fry things. So sometimes it makes sense to test things in isolation. And to talk to things via Python that are produced by Adafruit, they have a common set of library routines called Blinka that started out as MicroPython kernel things, but are now CircuitPython. So I used that. Didn't have to write a lot of stuff. Now, you remember me saying I was using NeoPixels and I went with DotStars. This gets into the minutia of it, but basically the driver of the NeoPixel interface made it where I couldn't reliably receive the microphone data. They have different interfaces. They buffer differently, is the best way to describe it. And here's where I recommend do not buy the cheapest, just the raw parts, the surface mount devices, because you'll find that soldering them with ham-fisted humans and home soldering stations and such is just, it's no way to go. So don't buy the individual chips. See down at the bottom on the right, there's a long flexible strip that the LED chips are already surface mount soldered into, and I just took scissors and then attached leads via solder to the ends, which is much easier. The interfaces you have to enable, it uses SPI for the DotStar. It uses a serial interface logic for that, so you have to turn on the UART, and then it uses I2S for the microphone. So you have to enable those interfaces and have those modules be loaded, and then you have to verify that they're actually there. And then this is my LED that emits the photons, my flux emitter. No, it's not a flux capacitor, it's a flux emitter. This is the NeoPixel one. It has 4 wires that go to it, and I deemed that not usable. So let's go on to the next one. Here's the DotStar. It has 6 wires. The numbers of wires is not the reason why I chose it. It's the driver for it was better behaved under Linux than was the NeoPixel's driver to make it where I could receive the microphone input. Lots of minutia into that, including pin numbers. And then installing the library support for them. And then debugging the interfaces. Is it there? Is it working? Yeah. Now, what I'm trying to do is to have the microphone detect the photons transferring momentum to the sensor of the microphone and getting the value off of that as if it was audio. Here's more details about the microphone device. You can see the pictures on the rightmost ones. Those are actually what I did. So I soldered some pin connectors onto the top side of the microphone, making the bottom side open for me to be able to shine light into it, LED light. And there's that, and pins and wiring and signal numbers. And then debugging the interface for it. That was a heck of a thing. I had to actually use my digital oscilloscope to, am I really producing the clock? Yes, I'm producing clock. How come no data is coming in? Turns out that was like a Linux configuration item. I got into a lot of debugging the microphone module. Turns out there's a file called a .dts file. That's the driver source file that is the glue between the hardware and the actual driver operating under the Linux operating system. And so the binary, the object, the DTBO file doesn't come with your Raspberry Pi. You have to go find it and compile it. And you don't have to make changes to it, just find it and compile it and then load it onto your system. So there's the instructions for doing that. Without that, it just don't work. And then if you want a primers, that is the audio work under Linux. I'm not going to get into the details of it, but there you go. And then the libraries associated with the higher level processing of audio under Linux and how to see if your interface is there or not. And then there's a file you have to modify to allow processes running under your login to see the devices. And then how to make those devices show up and confirm that they are there. Now, this one was kind of a red herring. You had to install the Adafruit MEMS microphone support. It turns out the Adafruit MEMS microphone does not really use the I2S interface. It uses something called PDM. So I went through this and then had to back it out. And that's what, here, look, we're backing it out. The interface is PDM, it's not I2S. And the description of, hey, different Raspberry Pis use different chips on their little motherboards, and the different chips clock at different rates. And so you needed different microphone drivers. Luckily, when they came up with the latest version called Bookworm, it automatically selects the right drivers for the right model Raspberry Pi that you're on. So details, but you don't need to worry about it if you're a Bookworm related. And then verifying that you can actually record with the microphone and play back the audio completely independently of the actual testing we're trying to do. So speak into the microphone, put music into the microphone. Can it record? Can it play back? That validates all the hardware, all the drivers, all the application interfaces. So if you can do this, you've got a working microphone. Now, the data coming off the microphone is something you've got to record it to a file for our testing purposes. It's not like, playing music. It's, I want the data, not the sound. Get the data, store the data in a file so I can analyze it. To do that, you need a lot of basically libraries that Python can talk to. One of those libraries is called NumPy. It's NumPy or NumPy. It is direct C library routines talking to the operating system to transfer high volumes of binary data. So when you're getting stuff like streaming audio in and you want to pump that into an array that you can then analyze, you use NumPy to do that because it's a high performance way of doing it. And it creates object accessible things from Python. One of the things that NumPy needs is something called BLAS. It's a linear algebra mathematical library. And the particular version it uses, the particular type it uses, called OpenBLAS. It's a linear algebra library, and NumPy requires it. But when you're installing NumPy, it won't tell you, I didn't get my BLAS. You go to run NumPy and it says, error, danger, Will Robinson. Please read this for advice on how to solve this issue. And turns out I just had to install OpenBLAS and problem solved. Now that we've got, audio that we can store, how do we analyze that stuff? How do we look at the data? You can do all sorts of things to it, but you have to recognize what might be erroneous data. So, putting it in the vacuum might have been a way of doing that, but you can do other things too, like, what I did, which is phone blocks. And you just seal it under the phone block and close it off from outside sounds. But, the things that you don't think of as being noise subliminally just is there, like the fan of your laptop coming on, going off, making little humming sounds. You don't notice that, but the microphone over here can hear that. So you have to identify those things. So the way you know that is you record when you make your changes with a timestamp. You record the log of you making the changes. You record the waveform to a wave file. And then you can play the wave file back and look at like where the peaks and valleys are, and then know the timestamp. When you started recording, you got a timestamp. You know the speed of the recording, so you know where all the edges of everything are, and you know from your log file where the timestamps are. So that's how you judge, was it me or was it Memorex? Fans, your home air conditioning unit, the fan comes on, the fan goes off. You don't notice it, but the microphone will record it. Room lights, if you got a fluorescent light that has a hum to it, it'll pick up the hum. Have you got a TV that has a hum to it? If your compressor for your AC unit is a little out of alignment, it can induce vibrations in the foundation of your house that you will likely never perceive. But if you're doing your microphone measurements on a steel table that has direct contact with the floor of your house, let's say in your garage, the microphone's going to pick up those vibrations, even though you can't hear them. All kinds of things you have to say, I need to prove that it wasn't that. Now, when an LED produces its photons, it doesn't produce them in a beam like a laser. It emits them over a wide range so that you can see lots of light from the little tiny LED chip. The particular LEDs that I'm using, they have a 120-degree dispersion angle. So there's 90. If I did 60 and 60, there's 120. So if I take the LED emitting light and I put it directly in front of that little tiny microphone hole, not all of the photons coming out of the LED are going to be hitting the microphone's input. So I have to get that light as close as possible without touching it, without electrically contacting it. So the LED producing the photons was 5.5 millimeters away from the microphone input port. Now, if I'm going to be doing, LED, photon, microphone, detection, recording signal, I need to make sure all the individual components are working. The power and ground is working. The clocks at the interfaces are working. All that stuff's working. All the software libraries are working. So I need something that will test the LED all by itself in isolation, test the microphone all by itself in isolation, and then I can claim connected testing. So I wrote a little Python script that will test the LED. And then I wrote a script for testing the microphone. And then I had to isolate background noise that I could identify. And the way I did this was I took the audio that I recorded before I started recording for real. I did some test audio recording, and I saw noise. I amplified the noise 1200% so that I could see, like, oh, now that I can hear it, it sounds like my laptop. So I would recognize that's the fan in my laptop. Or I would recognize, oh, that's the fan out in the garage, or any of those sorts of things. Be able to know what you're listening to. The best way to do that is amplify the audio that you're testing with to the point where you can hear what normally would not be perceivable because it's just background noise. So how did I isolate it? Here's my foam block technology. I took some high density polyethylene foam, not polystyrene, because that reverberates. I used polyethylene, which has little air inside of little tiny bubbles to dampen any sound reverberations. I put a block underneath the LED and microphone assembly, and then I put around it, and then I put a plug of that foam in over the top of it. And that's how I made my actual recording observations. Anything else that I could find, I found a way of mitigating it. And this one took some analysis. This is the whole NeoPixel basically locking process execution from the microphone driver and how that presents itself. So how did I correlate the two? Timestamps of my logs, knowing what I sent in, recording in the log what changes I was making, and then aligning that timestamp wise with the signals that I was seeing in the waveform. So I went to do the actual testing and I said, okay, let me make it quiet. Let me start the changes to the lights. It's driven by the Python script. I don't have to tell it to proceed at some step. It has a plan that it runs through of light changes, records it all while it's doing it. So it starts the sound recording, and then it makes the light changes, and then it stops the sound recording. And before it starts making changes and after it starts making changes, there's a kind of a audio silent spot. And then between power level changes of the red, green, blue, and white outputs, there are also null spots. And I made those different lengths so that they're discernible. But I didn't need the vacuum. The DotStar was sufficient. I didn't need to fancy things up. But I got data. And here's the data. As people would say, show me the data. Well, I've got the data. It's stored in files that I've marked read-only, so I'm not going to lose it. I understand the signal. The next slide we'll get into signal analysis, but you can see the log on the left, and I made it in different colors so you could see the red, green, blue, and then gray for white. Value changes. So you can see that when the value increases, the amplitude of the signal changes. And I can explain why it kind of diagonally notches off. You would think it'd be flat, but it diagonally notches off. And there's an explanation for that. And the vertical long blue lines, those are known as spikes or ring, and that's in the actual voltage levels of the LEDs. You don't see that when the light changes, like when you tell an LED to turn on. the spike is such a short duration, you don't notice that the LED gets really bright for a very, very brief period of time before the light level stabilizes out. The other thing you can see here is you see it says red, green, blue, and grayscale. Notice the height of the peaks. Remember that red is lower energy than is green, which is lower energy than is blue. But if I add all of red, green, and blue together, it should be even higher than the blue. And that's exactly what you see. You see the height, the amplitude of the signals, red, green, blue, grayscale, or white. So there was a direct correlation. And then I went on to explain, okay, why does the signal look the way it does? And you can see the timestamp markers. I can go into my sound editing software and actually put a line down and say, at what time spot is this? And then I can go look in my log text file and see what did I do at that point. So I can see it from microphone turn on to 0.856 seconds is the point at which I made the LEDs red, green, blue change to be 12800, which is 128 red, 0 green, 0 blue. And you see a certain level. When I changed that level from 128 to 220, it went up. Well, notice at the same time it went up, the peak of it started getting diagonal. It started like flattening on the top. And when I went to 255, it didn't get as bright as it used to be. It continued this diagonal decline. And it turns out that's due to the charge pumping at 1.2 kilohertz of the LED chips. They monitor their temperature. And when the LED starts to become inefficient, they actually reduce the power going to it. So it looks brighter, but it's actually using less power. So on the right side here, you can see the values, 32, which didn't show up, 128, 220, and then 255. And you can see the constant amperage, the constant current power of the LED versus the reduction, the varying in voltage. And then you can see the on-off, those switching vertical spikes. And also, if you look at the actual tall amplitude, you'll see it's not flat. It's not round. It's kind of like a bunch of little vertical spikes. That's the charging cycle of the LED power pulsing. That's the individual lines that are turning off and on. So I said, well, I need to be definitively pointing this out. Now, the reason why it's green and not blue is just that's the software that I was using. When I load different samples, it'll change the colors so you can see different things. But it's the color change is irrelevant. I could make it purple if I wanted to. That's not a change in the signal. But I purposefully changed the individual, I ran a different test with different values. I changed the individual channels by on almost to the top, but not quite to the top. And then I started from no output at 0, and then went to the output, and then went back to 0 for a period of time to allow the LED chip to cool off so that I wasn't getting like too much of a trim down. And you can see on the green, blue, and certainly on the grayscale, the power level certainly came down. But the time period at which the power was on that made the peak signal versus the time period it was allowed to cool down, those two time periods were different. So when it's on, that's the X period of time, that width. And when it's off, that's the Y period of time. And you can see that Y is noticeably wider than X. So I could actually see in the audio signal that's being recorded the distinctive values of wavelength, the distinctive periods of on versus off. You can see it in the data as the saying goes. So they went through the analysis of, okay, I've seen what I think it might be. What might it be other than what I think it is? So we'll go through the details of those, which is infrared heating. This is always a good one in physics. You're seeing like a heating of your wiring or heating of the LEDs. And okay, one thing you need to know about smart LEDs is they always have the power applied, even when the LED is off. because they're refreshing. They're like, refreshing the display. As the display values change, they have to have a constant refresh rate. So the wires are always under a voltage. So the wire heating wouldn't change dramatically. And as you can tell, even in the background, there's a little bit of noise, but that's amplitude background. The wavelength change made the amplitude change. So it's not the infrared heating. And also, if it were something like a fan, that would be a sinusoidal waveform. And I actually have a difference in waveform based upon what color I'm using. And oh, by the way, you could even see that the green channel ANSI lumens, because green is perceived as so much brighter, the ANSI lumens were actually less, the amplitude was less than the red channel. It's not a power surge. So you saw the spikes where the power is turned on, the power is turned off to the individual LED chips. It wasn't that, because there's a value in between. And remember, the power is always on, it's always refreshing. So the surge would be damped. It's not radio frequency interference. I actually have an inductive choke on the signal wires going to the microphone so that there's no RFI hash coming off of the computer or other things that can make it down the wires to the microphone that would affect the microphone's analog to digital converter. And obviously it's not gravity because I ran the emitter and transducing sensor horizontally to mitigate anything that people might say. It must be gravity affecting the photon. So in summary, I've tried doing the analysis of radiation reflection pressure for several years now. And it's always a matter of the time it takes to go do the negotiation to get access to a professional lab, the cost of doing it, trying to do it on my own, how much the equipment is going to be, how much effort, how precise do I need it to get to the nanonewton level. But what I've demonstrated in this project is there are repeatable observations, and you can explain out any outside sources. And if you doubt that momentum transfer has an effect, then optical tweezers, and I didn't need any lasers, so even better than optical tweezers. And we could also see in the data that when I change the wavelength, the amplitude changed, so it's color discernible. And I could do this at normal pressure. I did not need to use a vacuum chamber, and I could use less than 1 watt LED, so I didn't need massive output of LED photons. And I could measure it directly with one microphone without a whole bunch of external amplifiers and such, and using 44 kilohertz audio sampling. The effects were directly noticeable. I could correlate the log timestamps to the waveform change timestamps in the audio analysis software. So in me, it's like, check it, done. Now it's time for others to look at this video, maybe request the PDF so they get more details, maybe request my Python scripts if they really want to see something. There you go. Time for others to give it a chance to try it out. Not that expensive. And report back. Tell me something I forgot to take into account. Point out that you did even better. That would be good. Peer review time. It's cheap. It's easy enough to do. I can give you the stuff you need. I can give you the observation files and repeat it, confirm it, improve the results. But I can do this even better. How do I get the more light to come out of the LED to go into the microphone chip? Well, then I had to study the emission angle. The curve in the upper right is actually from the manufacturer of the LED chip saying, when we produce light out of our part, the light fans out to this angle. So you can see 0 to 60, and then it declines after 60. So 60 on one side of the chip and then 60 on the other side gives you your 120 degrees. And if you look at my 4 millimeter wide LED and the 5.5 millimeter separation between the LED and the microphone, there's your emission angle. And you can see that only that darker pink is the photons that actually make it up from the LED into the little hole in the printed circuit board, into the hole in the microphone chip. I didn't need huge wattage to actually make the data apparent in observations. But if you said, I'm going to go get a 50-watt LED, you'd probably burn up the microphone. And then, of course, I had to analyze okay, how can I get rid of these signal noise items? The fact that 32 was not observed. Well, that's a threshold on the microphone, not enough energy impacting the microphone because the microphone has filters in it. So it will reduce background noise levels. Well, apparently my 32 value LED was too low into the weeds. So the microphone actually clipped that. So how do I improve that? I just start with a number greater than 32. How about 64? Okay. The spikes, the power spikes off and on, I could start at a value of 0 and then slowly increase the voltage instead of, spiking it. The charge pump lines, those thin vertical changes, I could get an LED that didn't use that was a dumb LED, not a smart LED, and I could drive it directly. Of course, the brightness will vary because I'm not doing the power and temperature monitoring, but it would get rid of the spikes. And the decline in amplitude over time, same thing. If I get a dumb LED and I drive it directly with a constant current driver, I could dampen that out. And then the green amplitude being different than the red or the blue, yeah, I could ignore the ANSI lumens buffering and just drive the green as much as I drive the others. The green will be incredibly brighter to the human eye, but it shouldn't change the energy output going to the microphone. It should actually make red, green, blue. And then the LED, I could change it from being a DotStar to being a dumb LED that I drove directly, where I would have individual wire controls over the red, green, blue, and white chips. This actually has 4 chips inside the device, 1 for each color, red, green, and blue, and 1 for white. Now, if you're curious, the chip in the upper right-hand corner, not the device is all 4 of those chips, but the yellow-looking little square inside the device is the white one, because the chip is actually producing a particular wavelength of ultraviolet, and then it's got a phosphorescing material layer on top of it, and that causes it to produce a broad spectrum of white. That's how white light bulbs work in your house nowadays, is the individual chips are deeply ultraviolet, and then the plastic covering on the outside of the bulb has a fluorescent material that makes it white. And I could use a different microphone. A microphone without that filtering on the front end would pick up lower levels, and I could put my own amplifier on it and drive it higher. But that's a lot of extra complication and cost, which I picked up the signal just fine with the microphone that I use. So if somebody really wanted to get serious about it, they could do these kind of things. The parts aren't that expensive. And then yours truly. And lots of links about links about links. And then if you want to know what a NeoPixel is and all about it, even though I decided not to use them, there's information about NeoPixels. And then the microphone I was going to originally use, and then the one I actually used. And then the computer, and then software on the computer. How to get the microphone and the audio working. The trouble with NumPy and OpenBlast. And then if you wanted to know the software that I used for the actual audio spectral analysis, it was just, audio wave file processing software from a company called NCH down in Australia. The product is called WavePad. I just happened to use that in conjunction with my video editing software, which also comes from NCH. They work well together, so Wavetech. You can use other things. The sound doesn't care. Okay. That was a long one that I did quickly, so feel free to review it all over time. And, members were given the PDF already, so they could waltz through it slide by slide if they wanted to. I know it's lots of minutia. I know it's lots of technically geeky things and computer things and software things and electronics and such. So comments, questions?
I have a comment and a question.
Yes.
First part is the comment, and I have my question. Okay. My comment first is, as several times you talk about different I think I know more today than I did 10 years ago about the topic that you talked about.
Okay.
But I mean, it's still, there's a lot that goes over my head, I know. And it's not because of you. It's just that I don't know a lot of these different things and I don't work with it. And I'm not planning to go out and buy these things and work on it, but it still intrigues me. And that's where my question comes up next, is that in my mind's eye, if I ever could do this in my own home, there must be some, what I hear is mostly pros. I don't know. You may have said some cons about doing this in your own home, but I don't know. There must be some cons that you might want to point out, that just to make sure that they're safe, when they're doing it in their own home, that you might not do certain things.
To my understanding of it all, and I've spent a lot of time understanding it all, it is perfectly safe to do it in your home. The parts are not licensed. You can buy them on Amazon or from Adafruit, get them delivered to your home. If you have the wherewithal of connecting it up, or can learn the skills to connect it up, there's a small amount of soldering to put pins on things. But even as I said, don't do the surface mount parts. Get them on a board already and then just connect up to the board. Yeah, I mean, you can do them at home. They're not that expensive. Overall, it's not thousands of dollars, certainly. Maybe $100+ for all the parts. You get to reuse things you already have, like displays in your laptop and windows and those kind of things. So it's doable by the individual do-it-yourselfer. Individual do-it-yourselfers have a lot more skills. I know the content creator types on YouTube, they're a lot more skilled in this than I am. There are, as they call them, white hat hackers that do work a lot with the electronics, that they would readily comprehend this. And if one of them watched it, they would go, I'm going to reproduce what he did, just to see if they can reproduce what I did, because it doesn't take that much. So we'll see once I put the video out there for the public to consume, if there's any desire for it. But as I say, my goal in doing it was to prove that I could measure it, I could detect it, and I've corroborated that. The second thing is to get it out to the public, and I think the Broad Astronomy public YouTube channel will do that, and see if anybody on the entire planet has, either willing to learn, has the skills, already maybe has most of the parts and can do it and just go, hey, I did what you did. I didn't find it to be that. It was this, or explained as that, or I've confirmed what you did. Yeah, it's pretty amazing that photons, which you don't think of as having much force, can actually be measured as audio. So, yeah.
Thank you. I appreciate it.
Sure. Nobody's born knowing this stuff, and they keep changing it all the time. But if anybody, when you see the video, if anybody has any questions about how something was done, or they get some of the hyperlinks and they still want to have another question asked, sure. That's what the comment section is for below the videos, is you can complain, but you can also ask. Comments or questions before I stop recording?